Good morning, dear students. Welcome back again with a new session of Science 1. Already we have discussed about high Earth orbits, that is height from the Earth's surface greater than 35,780 km. Dear students, before we start with it, I would request that the clarity of this video may not be very much clear. So, whenever I teach or explain about the science with respect to textbook, I suggest you that please be present with the textbook so that you would be able to understand whatever I am saying. So again, I'll start with that part which in the previous video partly I have completed. High Earth orbit. If the height of the satellite orbit above the Earth's surface is greater than or equal to 35,780 kilometers, the orbit is called as high Earth orbit. As we all see in the next solved example, a satellite revolving in an orbit 35,780 km above the Earth's surface will take around 24 hours to complete one revolution. We know that Earth also takes 24 almost hours for one revolution. The satellite is revolving in an orbit parallel to the equator. The time of revolution for the Earth around itself and for the satellite to revolve around the Earth being the same, the satellite will appear to be stationary with respect to the Earth. Now, for a passenger in one vehicle, another vehicle moving parallel to him with equal velocity appears to be stationary. This is what happens here also. These things are called, therefore, geosynchronous satellites. Since these satellites are stationary with reference to the Earth, they can observe a specific portion of the Earth continuously. Therefore, they are used in applications like meteorology and for carrying signals of telephone, television, radio, etc. So here, the motion of the or the movement of the artificial satellite, that is apart from moon. Moon is a natural satellite. The revolution takes place 24 hours around the Earth. Same way, Earth revolving in its own axis is also 24 hours. Both the satellite is located exactly at the equator, and since the movement of the Earth and the satellite is approximately same, to moving with 24 hours one revolution, and therefore both appears to be stationary, like it is compared with the two trains traveling in the same direction with the same speed. Both the train appears to be stationary. Now, medium Earth orbit, height above Earth's surface 2000 km to 35,780 km. If the height of the satellite above the Earth's surface is in between 2000 km and 35,700 km, 35,780 km, the orbits are called medium Earth orbits. The geostationary satellites orbits above the equator. These are therefore not useful in the study of polar regions. For this purpose, the elliptical medium Earth orbit passing over the polar regions are used. These orbits are called as polar orbits. In these orbits, satellites complete one revolution in 2 to 24 hours. So in the previous case, it was full 24 hours, and in this case, where the height is very much low as compared to 35,780 km, therefore the satellite takes near about 2 to 24 hours for one revolution around the Earth. Some of these satellites revolve in circular orbits at a height of about 20,200 km above the Earth's surface. Global positioning satellites revolve in such orbits. Low Earth orbit, that is height above the Earth's surface, is 180 to 2000 km. If the height of the satellite orbit above the Earth's surface is between 180 to 2000 km, the orbits are called as low Earth orbits. The satellites used for scientific experiments and atmospheric studies revolve in low Earth orbits. Depending on the height of the orbits, they complete one revolution in 90 minutes. International Space Satellite and Hubble Telescope also revolve in low Earth orbits. The figure 10.4 shows the various orbits of satellites. You can see the diagram here. Uh, LEO, low Earth orbit, ranging from 180 to 2000. Then MEO, ranging from 2000 to 35,780 kilometer, and HEO, ranging up to 35,780 kilometer. Now these short examples, which is not there in our syllabus, so excluding this, we'll try to move ahead with the satellite launch vehicles. Satellite launch vehicles are used to place the satellites in the specific orbits. The functioning of the satellite launch vehicle is based on Newton's third law of motion. The launch vehicle uses specific type of fuel. This gas produced due to the gas produced due to combustion of fuel expands due to its high temperature and is expelled forcefully through the nozzles at rear side of the launch vehicle. As a reaction of this, thrust acts on the vehicle, which drives the vehicle high in the space. Now here, in order to launch the vehicle, Newton's third law of motion is being used. Now, how the third law? The vehicle moving in a downward direction. As a result of this, the force is applied on the uh, forces are applied on the vehicle, and it moves in the vertically upward direction. The structure of the launch vehicle is decided by the weight of the satellite and the type of the satellite orbit. The fuel of the vehicle also depends on these factors. So depending upon on which orbit it has to be placed, HEO, MEO or LEO, and depending upon the weight of the satellites, the the position of these satellites are being affected. The fuel of the vehicle also depends upon these factors. So requirement of fuel also will affect it. Definitely, if it is HEO, the requirement of fuel will be more, and if it is LEO, the requirement of fuel will be very less. Thus, the vehicle has to carry a large weight of the fuel with it. To overcome this problem, the launch vehicles with more than one stage are used. Due to this, the weight of vehicle can be reduced step by step after its launching. For example, consider a launch vehicle having two stages. For launching a vehicle, the fuel and the engine in the first stage are used. This imparts a specific velocity on the vehicle and takes it to a certain height. Once the fuel in the first stage is exhausted, the empty fuel tank and the engine are deducted from the main body of the vehicle and fall either into a sea or on an unpopulated area. So here in the first stage, what happens? The weight of the vehicle is reduced by detaching the part which contains fuel. As the fuel in the first stage is exhausted, the fuel in the second stage is ignited. As soon as the first stage fuel is exhausted, खत्म हो गया, तो दूसरा और उड़ने के लिए fuel tank is required. So as the fuel of the first stage is exhausted, the fuel of the second stage is ignited. However, the vehicle now contains only one, that is the second stage. The weight has now been reduced. The vehicle can move with a higher speed. Almost all vehicles are made up of either two or more stages. As an example, the structure of Polar Satellite Launch Vehicle, that is PSLV, developed by ISRO of India, is shown in figure 10.5a. You can see here it is made up of four stages, and in each and every stage that part of the vehicle is being detached so that the weight of the vehicle is being reduced step by step and the velocity of the vehicle increases step by step. Now how these parts get detached itself, that can be shown here in the picture 10.5b. So launch vehicles are costly because they can be used only once. USA has therefore developed a space shuttle which returns to the Earth except for the fuel tank that can be reused in multiple of launches. So used fuels can be used again and again if it is brought down safely. Space missions away from the Earth. As we have as we have seen above, artificial satellites are being used for making our life more and more enriched. However, in the previous standard, we have learned about how the telescopes aboard artificial satellites are used to gather information about various objects in the universe. Similarly, some space missions are used to gain further knowledge about the universe. In these missions, spacecrafts have sent to the nearby objects in the solar system to observe them more closely. New information has been obtained from such missions and is helping to understand the creation and evolution of our solar system. For such missions, the spacecraft must escape the Earth's gravitational force to travel into the outer space. To achieve this, the initial velocity of the moving object must be greater than the escape velocity of the Earth, as we have learned in the chapter on gravity. Escape velocity on the planet can be obtained by using following formula. Escape velocity equals to under the square root of 2 gm upon r, where g is gravitational constant 6.670 10 raised to minus 11 Newton meter square per kg square. Mass of the Earth or mass of the planet is 6 into 10 raised to 24 kg for the Earth, and radius of the planet is 6.4 to 10 raised to 6 meter for the Earth. And after putting up the values, we get the escape velocity is approximately 11.18 kilometer per second. Thus, if a spacecraft is to escape the Earth's gravitational force, the travel of the outer space, it must have minimum velocity of 11.2 km per second. The astronomical object closest to us in the moon light takes place is 1 second to reach from moon to the Earth. It means that if we travel with the speed of light, it will take 1 second to reach the moon. However, since a spacecraft travels to such a smaller speed, it takes longer time to reach the moon. The shortest time taken by a spacecraft to reach the moon so far is 8 hours and 36 minutes. Remaining part of this lesson we'll do it in the next video. Till then, have a great day.